Welcome to the SAT Math Quadratics Masterclass. In the next 20 minutes, you'll learn everything you need to confidently solve any quadratic problem that appears on the SAT. We'll cover vertex form, completing the square, factoring, the quadratic formula, and finish with a quick practice session. Let's get started. Before we dive into the techniques, let's take a moment to understand why mastering quadratics is so important for the SAT. Quadratic questions appear in both the calculator and no calculator sections, and the test expects you to switch between factoring, completing the square, using the quadratic formula, or recognizing vertex form instantly. The truth is that most students struggle not because the math is too hard, but because they don't know which method to use or how the pieces connect. In this masterclass, we'll slow things down and build a complete, intuitive picture of how quadratics behave, how their graphs work, and why each solving method fits into the bigger framework. By approaching the topic step by step, you'll develop the kind of deep understanding that makes the SAT feel predictable instead of overwhelming. This foundation will make every skill we practice later, from factoring to the quadratic formula, much easier, faster, and more confident. Before we begin solving equations, let's build a solid visual intuition for quadratics. A quadratic is any expression shaped like a parabola, and its structure follows the form ax squared plus bx plus c. Understanding these three coefficients is absolutely essential for the SAT. The number A determines whether the parabola opens upward or downward, and it controls how wide or narrow the curve appears. When A is greater than 1, the graph becomes steeper. Imagine the parabola being stretched vertically, making it narrower. When A is between 0 and 1, the graph widens out. The parabola becomes flatter and more spread out. And if A is negative, the entire parabola flips upside down, transforming from a U shape into an upside-down U. The value of B affects where the parabola tilts left or right. It might seem less obvious at first, but B works together with A to determine the exact x-coordinate of the vertex, the turning point of the parabola. This is why you'll see the expression negative B over 2A appearing frequently. Finally, C tells us the exact point where the graph crosses the y-axis. This is the easiest parameter to identify. It's simply the y-intercept, the output value when x equals 0. The reason these parameters matter so much is that SAT questions often expect you to read the behavior of the graph without actually drawing it or calculating points. By knowing how A, B, and C shape the curve, you'll understand every technique we explore later, factoring, completing the square, and using the quadratic formula, much more clearly and intuitively. Now let's look at the vertex form of a quadratic, which is one of the most useful and powerful tools for the SAT. The equation y equals a times parenthesis x minus h parenthesis squared plus k has a very powerful feature. It reveals the vertex instantly, without any calculation. The point, h, k, is the lowest point of the graph if A is positive, or the highest point if A is negative. This immediate visibility is what makes vertex form so valuable. This form also tells us exactly how the parabola shifts and transforms. The value of h moves the graph left or right. If h is positive, the vertex shifts to the right, and if h is negative, the vertex shifts to the left. Meanwhile, k moves the graph up or down. Positive k shifts upward, negative k shifts downward. And just like before, the coefficient A controls both the opening direction and the steepness of the parabola. Why does the SAT use this form so often? Because it allows you to interpret graphs quickly and accurately. You can identify maximum or minimum values at a glance, determine symmetry without drawing the full graph, or compare two different parabolas without any lengthy calculation. By understanding vertex form deeply, you'll start to see quadratics not as abstract equations to manipulate, but as geometric shapes you can read and interpret immediately. This shift in perspective will make all the upcoming solving techniques, including completing the square, feel far more natural and intuitive. In this section, we'll learn how to factor quadratics. Using the AC method, a reliable and systematic technique that works consistently on the SAT. The process begins by multiplying A and C, which gives us a target product. This is the number we're aiming for. Next, we look for two numbers that have a very specific relationship. They must multiply together to give us this AC product, and at the same time, they must add up to equal the coefficient B. Once we find those two special numbers, we split the middle term of the quadratic accordingly. This transforms the original three-term expression into a four-term expression that's ready for the next step. Then we factor by grouping, taking common factors from the first pair of terms and the second pair of terms separately, until a common binomial factor emerges. Although this method may feel mechanical or procedural at first, it gives you complete control over quadratics that do not factor cleanly at a glance. Many students try to guess factors by trial and error, but the AC method eliminates guessing entirely. It's especially useful on the SAT, where expressions are carefully designed to test your flexibility and your ability to work systematically under time pressure. As you practice this technique, you'll find that the AC method becomes quick, automatic, and intuitive, allowing you to factor almost any quadratic without relying on shortcuts or hoping you get lucky. Now let's begin exploring the method of completing the square. This technique rewrites a quadratic into a perfect square expression, making it dramatically easier to interpret and convert into vertex form. We start with the basic structure x squared plus bx plus c. The central idea behind this method is to focus on the middle coefficient, b. If we take half of that value and then square it, we create exactly the number needed to turn the quadratic into a perfect square. This step might seem simple or even trivial at first, but it forms the absolute foundation of the entire method. Here's the clever part. By adding and subtracting this squared value inside the expression, we don't change the overall value of the expression at all. We're adding 0 in a strategic way, but we restructure it into a much cleaner and more meaningful form. At this stage, we are essentially preparing the quadratic, setting it up carefully for what will become a perfect square in the next step. Think of it like organizing puzzle pieces before putting them together. Once this structure is in place, we'll be ready to rewrite the expression in a beautifully compact form that reveals the vertex instantly and makes the geometry of the parabola completely transparent. Now let's see how completing the square transforms our quadratic in a truly powerful way. Once we add the squared value we prepared earlier and carefully rearrange the expression, the quadratic becomes a perfect square, something of the form parenthesis x plus a constant parenthesis squared. This is remarkably powerful because it immediately gives us the vertex form structure that we need. The completed expression takes the form a times parenthesis x minus h parenthesis squared plus k, where the value inside the parentheses tells us the horizontal shift, how far left or right the parabola moves from the origin, and the constant outside tells us the vertical shift, how far up or down the vertex sits. You will notice that this transformation is not just algebraic manipulation. It's not just pushing symbols around on paper. It is fundamentally geometric. It reveals exactly how the parabola moves and behaves on the coordinate plane. On the SAT, problems very often ask for interpretations of maximums, minimums, or graph transformations. Questions like, what is the minimum value of this function? Or, how does this graph compare to the parent function? Completing the square gives you everything you need to answer those questions confidently, quickly, and accurately, without having to draw graphs or make lengthy calculations. Let's walk through a simple, clean example. X squared plus 6x plus 5. First, we take half of 6, which is 3. Then we square 3 to get 9. To complete the square, we add and subtract 9 inside the expression, which keeps the total value unchanged. Now the quadratic becomes x squared plus 6x plus 9 minus 9 plus 5. The first three terms form a perfect square, so we can rewrite them as parenthesis x plus 3 parenthesis squared. The remaining constants combine to give -4. So the final expression becomes parenthesis x plus 3 parenthesis squared minus 4. From here, the vertex is easy to read, -3, -4. This example shows how completing the square turns the quadratic into a form that is extremely easy to interpret. Now let's try a slightly more challenging example, x squared plus 8x plus 3. We begin the same way. Take half of 8, which is 4. Square it to get 16. To complete the square, we add and subtract 16 inside the expression. This transforms the quadratic into x squared plus 8x plus 16 minus 16 plus 3. The first three terms form a perfect square, parenthesis x plus 4 parenthesis squared. The remaining constants give us -13. So the final result is parenthesis x plus 4 parenthesis squared minus 13. This example illustrates that even when the numbers aren't perfect or symmetric, the completing the square method still produces a clean and readable vertex form expression. Now let's step back and see why completing the square is such a meaningful technique. When you complete the square, you rearrange the quadratic expression so that the vertex becomes visible. The squared part is isolated, and the expression inside the parentheses becomes x plus b over 2, which reveals the horizontal shift of the parabola. This is why, when the coefficient of x squared is 1, the x-coordinate of the vertex is always -b over 2. Completing the square is the algebraic process that reveals this geometric truth. On the SAT, This connection allows you to identify maximum and minimum values quickly and to compare quadratic functions without lengthy calculations. Understanding why the technique works not only strengthens your intuition, but also makes every future problem feel easier and more predictable. Now let's look at the general formula that emerges from completing the square. Starting with x squared plus bx plus c, we take half of b, square it, and add and subtract that value within the expression. This transforms the quadratic into a perfect square plus a constant adjustment. Mathematically, this gives us parenthesis x plus b over 2 parenthesis squared plus c minus b squared over 4. This formula is extremely helpful because it provides a direct pathway from standard form to vertex form for any quadratic expression. Once you internalize this pattern, you'll be able to convert quadratics quickly and accurately, saving valuable time during the SAT. This is the foundation. Let's reinforce what we've learned with a few more examples that show how completing the square works across different types of quadratics. First, consider x squared plus 4x plus 1. We take half of 4, which is 2, and completing the square gives us parenthesis x plus 2 parenthesis squared minus 3. This is our vertex form, revealing the vertex at -2, -3. Next, consider x squared minus 7x plus 6. Half of -7 is -7 over 2. When we complete the square, we get parenthesis x minus 7 over 2 parenthesis squared minus 25 over 4. Notice how the technique works even with fractions and negative coefficients. These examples demonstrate a powerful truth. Any quadratic expression, no matter how it's written, no matter what the coefficients are, can be converted into vertex form through completing the square. This universality is what makes the technique so valuable. Whether you're dealing with simple integers or messy fractions, positive or negative values, the process remains exactly the same. You're always building toward that perfect square structure that reveals the vertex immediately. On the SAT, this means you have a reliable tool that works in every situation. You never have to worry about whether a quadratic is too complicated to handle. Completing the square always works, and that consistency gives you tremendous confidence on test day. Now let's examine an important variation, cases where the coefficient of x squared is not equal to 1. When we start with ax squared plus bx plus c, where a is something other than 1, we need to add one preliminary step at the beginning. The first step is to factor out the value of a from the first two terms, the x squared and x terms. Once we've factored out a, we're left with a simpler expression inside the parentheses. Inside those parentheses, we follow the exact same procedure as before. We take half of the new coefficient of x, which is now b over a, square it, and add and subtract that value. This allows us to rewrite the entire quadratic as a times a perfect square expression, plus a constant term that sits outside. The crucial idea here is that completing the square still works perfectly, even when the quadratic has a leading coefficient other than 1. The process is nearly identical, you just need that one extra step at the beginning to factor out a. Recognizing this pattern will help you handle more advanced SAT questions confidently. These are questions that involve scaling, stretching, or compressing of parabolas, transformations that change the steepness of the curve but don't change the fundamental shape. Any quadratic works with this method, even when a is not 1. That's the power of understanding the technique deeply rather than just memorizing steps. Now let's turn our attention to one of the most famous and powerful tools in algebra, the quadratic formula. It is used to find solutions to the equation ax squared plus bx plus c equals 0. The formula states that x equals negative b, plus or minus the square root of b squared minus 4ac, all divided by 2a. What makes this formula so remarkably powerful is that it works on every single quadratic equation, absolutely every one. Even quadratics that refuse to factor, even ones that produce irrational or complex answers, even those with coefficients that seem impossibly messy, the quadratic formula handles them all with perfect reliability. On the SAT, the quadratic formula is especially useful in several specific situations. First, when the numbers are messy or don't factor cleanly. Second, when a question asks for an exact value involving radicals or square roots. And third, when you need to be absolutely certain that you're finding both solutions correctly, without the risk of missing one through factoring errors. Before we jump into applying the formula, let's take a moment to understand each part of the formula and what it reveals about the nature of quadratic solutions. By understanding the structure, you'll use it more effectively and avoid common mistakes. Now let's see how to apply the quadratic formula step by step. We start with a quadratic in standard form. For this example, consider x squared plus 5x minus 14 equals 0. Step 1. Identify the values of a, b, and c. In this case, a equals 1, b equals 5, and c equals negative 14. Step 2. Write out the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Step 3. Plug in the values for a, b, and c. Step 4. Solve for x using arithmetic. By following these steps carefully, you can apply the quadratic formula to any equation efficiently and accurately. Now let's apply the quadratic formula to a real example. Consider the equation x squared minus 5x plus 6 equals 0. In this case, a equals 1, b equals negative 5, and c equals 6. Plugging these into the formula gives us x equals 5 plus or minus the square root of 25 minus 24, all divided by 2. The square root simplifies to 1, so the two solutions are 3 and 2. This example shows how the quadratic formula produces clean solutions even when the expression does not factor easily at first glance. Now let's try a more challenging example where the discriminant is not a perfect square. Suppose we have 2x squared plus 3x minus 7 equals 0. Here, a equals 2, b equals 3, and c equals negative 7. Substituting these into the quadratic formula gives us x equals negative 3 plus or minus the square root of 9 plus 56, all divided by 4. The discriminant becomes 65, which is not a perfect square. So the solutions simplify to negative 3 plus or minus the square root of 65, all over 4. This is a very typical SAT result, and being comfortable with irrational answers will help you score higher. Now that we have explored factoring, completing the square, and the quadratic formula, let's talk about choosing the best method during the SAT. If a quadratic factors cleanly, factoring is almost always the fastest approach. If the question asks for the vertex or involves transformations, completing the square or using vertex form will give you instant insight. And if the numbers are complicated or the expression does not factor, the quadratic formula is the most reliable method. The real skill lies in recognizing which tool fits the situation. By practicing these decisions, you'll be able to solve problems quickly without wasting time on unnecessary calculations. Congratulations on completing this SAT Math Quadratics Masterclass. Over the past 20 minutes, you've built a comprehensive understanding of one of the most important topics on the SAT. You've learned how to factor quadratics using the AC method, how to complete the square to reveal the vertex, how to interpret vertex form to understand graph transformations, and how to apply the quadratic formula to solve any equation, even those with messy or irrational solutions. But more importantly, you've developed the ability to recognize which method to use in different situations. This strategic thinking is what separates students who struggle with quadratics from those who solve them quickly and confidently on test day. The most important next step is practice. Try working through official SAT-style problems and apply the techniques you learned today. Pay attention to the patterns. Does the quadratic factor cleanly? Does the question ask for a vertex or maximum value? Are the numbers complicated enough to require the quadratic formula? If you want to review any section, feel free to go back and replay the parts that need reinforcement. Each time you review, the concepts will become clearer and more automatic. You're now much better prepared to tackle SAT quadratic questions with both confidence and speed. Quadratics appear frequently on the test, and mastering them gives you a real advantage. Keep practicing, stay focused, and trust the process. You've got this.